Mr. Tarrou. In this video, we are going to learn, well, possibly nothing. The purpose of this video is to just revisit and practice, fine-tune, hone our skills of using the basic integration rules. And we've had quite a few. I'm going to give you a chance to freeze the video here a second and copy a total of 20 integration rules that you will need to have memorized, especially if you're taking some kind of standardized test like the AP Calculus exam, which is what I'm teaching this year for the first time, AP Calculus AB. They don't give you any formulas at all. All of this stuff has to be memorized. Now, sometimes we have needed to do like a completing the square process to get our problem to match one of these integration rules. We have had to add and subtract something to the numerator to make it match, maybe expand the numerator. We're going to revisit all these algebraic techniques that we've used to make our problems match these integration rules. And some teachers that I've seen, and I'm even starting to do it a little bit myself, where some of the simpler problems, I'll do a little bit of manipulation to create the chain rule process in the expression which I'm trying to integrate so I can go right into the answer. But most of the time I still prefer to do a U substitution and work it down, simplify our problem that we're trying to integrate, and use that U substitution until I get it to be an exact match to that integral expression, and then go to the other side and write out the answer. And of course, if you're doing a definite integral and you go into a U substitution, you don't need to have this constant of integration. You're just looking for numerical answers. So don't forget to change your lower and upper limits and put them in terms of U as well if you're doing that process where you're getting that expression, removing all references to whatever the original variable is, probably x, and getting it in terms of or with reference to U. So let me step out, copy these examples or rules. And if you needed to copy them, you probably already just paused the video and did so. These are the last three, my fancy picture-in-picture. And so far, in the calculus book that I'm teaching out of, these are the 20 basic integration rules that we've had up till now. And there's other ways of integrating, like you can integrate by parts, but that is not on the Calculus AB curriculum. So at least for that purpose and for what I've made in the videos so far, we are only looking at these basic integration rules. So I'm going to do about, 5, 6, 7 examples. Let's get to the first one right now. Our first technique, expand the numerator. And also, I forgot to write a footnote on the previous board. Anywhere that a showed up in those integration rules, it is assumed to be greater than 0. Okay, so we have a pretty basic polynomial in the denominator, and this is going to be a fairly straightforward example period, but I do tend to make my videos starting from the less difficult to the more so. So we're going to expand the numerator. Why? Because, well, there's a binomial being squared, and if I look at this pretty basic polynomial in the denominator, the derivative of this is going to be 3x squared plus 18x plus 27. So let's see if the numerator, once expanded out, becomes the derivative of the denominator. See if we can make that happen. So this is going to be the indefinite integral of 3 times x squared plus 6x plus 9 all over x cubed plus 9x squared plus 27x dx. Now sometimes we want to take this constant, or this multiplication of a constant and move it out in front of the integral symbol. But again, that first term is, as a derivative, 3x squared. So maybe if I just distribute this 3, something nice will happen. Since I wrote the example, I kind of know that it will. So we have the indefinite integral of 3x squared plus 18x plus 27. Our denominator, again, is 3x, well, not again. Let's actually copy the denominator. X cubed plus 9x squared plus 27x dx. So indeed, we do have that pattern where the numerator is the denominator, the derivative of the denominator. Now I can come off to the side and I can say let u equal this and du is equal this, dx, and rewrite this so that it's the integral of 1 over u du, or you could write du over u. You might even just write u prime over u. and just recognize, but if we just recognize that pattern for this particular question, then we know, hopefully, that the indefinite integral of du over u is equal to the natural log of the absolute value of our denominator, our u, plus c. All right, so bringing that up here, we have the natural log of the absolute value of x cubed plus 9x squared plus 27x, and you can't take a log any base, certainly, or a natural log of a negative number. So this needs to be wrapped up in a set of absolute value symbols. And that's perfectly fine, and that's very well perfect for the AP exam, or very well possibly your teacher. But if you look in the back of the book, this might not be the answer that you see. If you're checking your work with a CAS calculator, this is not what it's going to look like, or at least it is not what it looked like on my Inspire CAS. So what I did see was the natural log of, now I just got rid of the absolute value symbols, x squared plus 9x plus 27 times the absolute value of x plus c, or something to that effect. You know, why? Well, I can see why the x came out. All three of these terms have an x, and of course x can be negative, so you need a set of absolute value symbols around it. Why is there none around x squared plus 9x plus 27? Because certainly, if x is negative, this term will be negative. But this entire expression, well, this is a parabola with the 1 squared term opening up. And if you graph it with your calculator, if you maybe do negative b over 2a and find the x of the vertex and then find the y, or you can complete the square to put this in standard form, whatever. If you graph this parabola, it is opening up and it is always above the x-axis, thus this expression can never be negative. So I don't see any, that would certainly not tell my students to do it on the AP exam, because you don't get points for simplifying if it's an open-ended question. Maybe if it's multiple choice, you got to finagle it a little bit. But at any rate, that is the end of our first example and reviewing our first technique, trying to get our problems to match a pattern so that we can recognize what integration rule we need to apply to, integrate. Or obviously, we're going to be doing a lot of u substitution in this video as well. Next example. Second example and second technique. Separate the numerator. Almost like expanding, but you're going to break your problem up into a bunch of small integral problems instead of one big one, and that makes the process of integrating much simpler when you can do it. When to look for it? Well, this particular example, when we're going to go ahead and add these two terms, we're going to raise that to a power of 3. Sometimes that'll be a good idea, sometimes not. In this particular example, I might add a lot of work. Every problem's a little bit different. We're going to see that the denominator is just going to be a single term, and there's going to be a bunch of terms on top. So please remember it, and I'm harping on my own kids as I say this. When you see a very simple denominator and a bunch of separate terms on top, where clearly you can't just let u be the denominator and try and find a du, or that will help you work with the top, pull it apart, make a bunch of small little problems. Very often will greatly simplify the process. I'm going to step off, reveal the problem in small incremental steps. So if you want to pause the video and try it on your own first, that would be a great idea. So as we can see, and hopefully you did, we took x minus 1 and raised it to a third power, and we have an x cubed in the denominator. The x out front cancels with one of the three x's in the denominator, giving us x squared. And now we have a very basic denominator, lots of stuff going on in the numerator. Certainly there's not going to be any kind of u substitution to get the numerator to somehow match up with the denominator and have one of our integration rules work as a whole. But if we do x cubed divided by x squared, we get x. If we do negative 3x squared divided by x squared, we get negative 3. We have 3x divided by x squared, giving us 3 over x, and then minus Negative 1 divided by x squared is, of course, negative 1 over x squared. And if we were just learning how to integrate and using the properties of integration, then maybe I would expand this and write, a separate little integration problem, if you will, for each of these terms. But I'm just going to kind of skip that because I don't think at this point we need it. We're going to integrate x, and we're going to raise that power by 1 and then divide. So we have 1/2 x squared, negative 3x. And we're going to bring this 3 out front and remind us that the integral of 1 over x dx is the natural log of the absolute value of x. And using that power rule, bringing this 1 over x squared, bringing it up, we have x to the negative 2. Increase that by 1. We have negative 1. So negative 1 times 1 is negative 1 times negative 1 is positive 1 times, or plus, that comes out to be plus x to the negative first power, which then we can write, of course, as 1 over x. And maybe you just went straight from there to there. It just depends on how much. I'm showing every single step because I'm making a video, and I don't want you to be confused. So, that is the end of our second example, somewhat of a straightforward example. So let's get on to our third, yet a little bit more difficult. Bang! In this third example, we are going to introduce 2 more techniques that we can use to make our problem match, manipulate it till we recognize that pattern so we know what integration rule we need. We're going to complete the square, and we're going to add and subtract terms in the numerator. Now, there's a lot of techniques at our disposal. This is clearly a big hint as to what we're going to do with the problem. Our denominator is, again, a basic polynomial. It's got a degree of 2, and the numerator has a degree of 1. And that leads us to the idea that maybe the numerator is some form of a derivative of the denominator. And we have this like u prime over u situation where our answer would be the natural log of the absolute value of u, or whatever expression we have let u equal. Now, I'm going to need to erase this later because I'm going to run out of room. We're going to let u equal x squared plus 8x plus 20, and thus du is going to be 2x plus 8 dx. Well, that's good. We have a 2x here in our expression. We have a 2x over here in the numerator. But what we don't have is a plus 8, and we do have one over here. Now, if that were, say, a 5x, then I could divide both sides by 5 and then multiply by 2 and get some, maybe like a 2/5 du equals 2x dx. But that plus 8 there is a little, we have to handle that a little bit differently. So if I had a plus 8 in the numerator, I would have u prime over u. But I don't. Thus, you can. Of course, if you're going to add something, you have to subtract it to keep it balanced. I don't want to change the value of the expression, but I can add and subtract terms in the numerator. And that term for this particular problem is going to be plus 8. So if I can introduce a plus 8, now I need to then subtract by 8. I have made the numerator look different. I have not changed its value. And now I can also, I'm actually going to separate the numerator in this as well, so quite a few techniques actually, and thus we're going to get a pattern of u prime over u for part of our problem. We have the indefinite integral of 2x plus 8 over x squared plus 8x plus 20, and then we also have a plus, dx, don't forget that, plus the indefinite integral of negative 8 over x squared plus 8x plus 20 dx. Or I could bring that negative 8 out, or that negative out, and write minus with a positive 8. And I might even eventually feel like I want to take the 8 all the way out in front of, and move it out front of our integral symbol. So we do have over here now u prime over u. So this is going to be the natural log of the absolute value of this denominator. Actually, we're not going to need the absolute value symbols because this is positive, and that's positive, but I'll write it at first and then, I'll go to a regular set of parentheses, and that's why. But what do we have over here now? A constant, some kind of expression, some kind of x's going on, some kind of function, and another constant. Well, I needed my chalkboard space, so I had to erase almost all of my integration rules, but this is looking like it might be, and I know I just changed the light in my video here, the numerator is not just going to be some kind of derivative of the denominator, because we already know the derivative of the denominator is 2x plus 8. But du, some kind of derivative of a function, okay, so it seems like I've got no radical in the denominator, so that rules these out. I think we might be setting up for using this integration rule and having an answer of 1 over a arctan or inverse tan of u over a plus c. Because the a is a constant, the u is your function, and it's something being squared. So that square, let's see if we can't complete the square in the denominator and get it to match this pattern so we can apply it. We might actually end up, through the completing the square process, realize that the pattern is actually matching another integration rule. But let's see if that is where we're headed. And I'm going to put this board back so the light's better. I'm going to erase this u substitution now that we've used it to sort of see where we need to go in the problem and reveal the problem small steps or one step at a time. So again, now that you got a big tip on how we might be going with this problem, you can pause the video and try it on your own. So we took, of course, your b is the coefficient of the single degree term. Half of 8 is 4. 4 squared is 16. And I'm adding 16 and subtracting 16 within the same denominator. Or if you're really good at recognizing that perfect square trinomial pattern, maybe you could have just split the 20 up in a special type of way where we get a perfect, again, that perfect square trinomial that when we factor just ends up being, well, what's going to be a binomial squared that now I'm standing in front of. But I did go through that completing the square process because usually it is what we need to do. Now, again, I have my one integral that's really basically already set up to go. Still manipulating the second one. I went ahead and pulled that 8 out front because now that I have this x squared plus 8x plus 16 written in factored form, and it's x plus 4 squared, and again I wrote those integration rules up here that we're using, I can see that my u is x plus 4, and du, the derivative of that, is just going to be 1. So I want to move that 8 completely out front. And then our a is a constant and it's squared, so instead of writing 4, it's better to see it as 2 squared. And now our problems are in the perfect pattern to apply these integration rules, and we get the natural log of x squared plus 8x plus 20 minus, and so on. You can read that. Now, I just realized as I was going through this process, I misspoke a little bit because I said we would not need these absolute value symbols because when you square something, it's always positive. And I saw the plus 8 and said that was positive, but x could be negative. So this middle term could be negative, but then we have a plus 20. So again, like the previous problem, and it doesn't have to be like exactly the previous problem. Of course, we can have parabolas come through and pass underneath the x-axis, and thus you would have to keep the absolute value symbols. But if you do graph this, whether it's with a calculator or noticing again power of 2, positive leading coefficient, thus it's opening up and you find the vertex, whether it's by putting this into standard form or doing your little x equals negative b over 2a for the x of the vertex and then finding the y. At any rate, that parabola is always above the x-axis, thus it is always going to be positive, and we don't need those absolute value symbols. On to the next example. Next, we're going to be taking a look at dividing improper rational functions. Again, we have a rational function. Doesn't have any transcendental functions in it, or it's not irrational, but our numerator has a degree which is higher than the denominator. And very often with these situations, we needed to do long division. I guess, well, you could really argue I could do synthetic division here, but we needed to divide this out so that we have a expression which we're going to find an integration rule for. We're not going to see that right here with that top degree greater or equal to the denominator. So we're going to take x squared minus 3x plus 2 and divide that by x plus 1. So of course we're trying to get these first terms to match up, so we're going to multiply by x and get x squared plus x. And subtract, that's going to give us 3 minus 1, which is negative 4x. And now to get that x, of course, to equal negative 4, we're going to multiply by negative 4 and get negative 4x. And minus 4, because that's negative 4 times 1. Subtract and get 2 minus negative 4 is equal to 6. And if I haven't made any mistakes, if I knew where I was looking, okay, there we go. Then I can rewrite this expression as the indefinite integral of x minus 4, a remainder of 6, over x plus 1 dx. Now, actually, let me go ahead and do this. Let me rewrite that 6 out front. The indefinite integral of x minus 4 plus 6 times 1 over x plus 1. And this is actually, hope you're not getting tired of using this integration rule, but we again have 1 over x plus 1. Well, that doesn't really mean anything, but the derivative of x plus 1 is equal to 1. So we have, once again, the integration pattern where we have a u prime over u. So this is going to be the natural log of the absolute value of x plus 1 when we write our answer, which is the last step, which is to actually integrate, because this is ready to go. And we have a bunch of separate terms here. So the integral of x is going to be equal to 1 over 2, or 1/2 x squared minus 4x plus 6, not L, 6 times the natural log of the absolute value of x plus 1. And again, don't forget, where all these examples are going to be indefinite integration problems, your constants of integration. Now, of course, that is a line with a y-intercept of 1 and a slope of positive 1, so there'll certainly be some ways for this expression to come out to be negative, so don't please drop it around that expression. Don't write the natural log of x plus 1. It is the absolute value of x plus 1. Next example. Next example, and next two techniques. Use trigonometric identities. Multiply and divide by a Pythagorean conjugate, where you might just be saying conjugate, like I do, but that's what my book says. And actually, this problem is going to be, again, quite difficult, and we're going to need more than just these two techniques to figure out how we're going to integrate this expression. Now, I do have an integration rule for secant. The indefinite integral of secant of u du is the natural log of secant of u plus tangent of u plus c. But I don't just have secant. I've got secant x minus 1, and there's no way with this being in the denominator and wrapped in parentheses with the 2 out front, how am I going to separate it? Plus it is in the denominator, so how am I going to bring it up and just have it be simply secant u du? So this is going to be not how we're going to approach the problem. Now I've got some integration rules, some nice integration rules that do sine and cosine, and secant is 1 over cosine, but I can't just flip that up because, again, it's not just secant of x, it's not 1 over 2 secant x, it's 2 times 1 over 2 times secant of x minus 1. So we are going to rewrite this to be in terms of cosine, but we're going to have to go through a common denominator process. This is going to be the indefinite integral of 1 over 2 times 1 over cosine x minus 1. And I'm kind of leaving some space because I want to make this denominator just one fraction, because I see that I'm going to have stuff over a fraction, so I'd like to be able to flip that bottom fraction up, but I can't do that unless there's only 1. I can't do it when there's 2 because I'm going to skip the process of finding a common denominator, and that's just going to mess us up. So my 1 is going to become cosine over cosine with my dx. And now writing this, we have the indefinite integral of 1 over 2. I've got 2 times 1 minus cosine x over my common denominator of cosine x. Okay, well now I've got 1 over a big fraction, so I'm going to flip that up. And we're going to get the indefinite integral of, again, flipping this up, we're going to have cosine of x over, and let's just go ahead and distribute that 2 through, I think. How did I show it in my notes? Oh, that'd be the door, so let me go get that and we'll come back to our example. Okay, so we've got this flipped up. We got cosine over 2 parentheses 1 minus cosine x. And we're going to move that 1/2 or that 2 out front and make it 1/2. And we're looking at this, okay, well, are we ready to do a u substitution yet? Could the denominator possibly, again, with all those times I came up with a natural log function, could we say let's let u equal 1 minus cosine x? Well, then that means that du would be equal to, well, the derivative of 1 is 0, and the derivative of cosine is negative sine, so that would be the sine of x dx. No, I'm going to have a problem here because I've got just a cosine function on top and a cosine function of some format in the denominator, and if I do any kind of u substitution with the cosine function, I'm going to need to get rid of all that references of x and finish my u substitution. I'll need some kind of trig function. I'll need sine in there, and I don't. So here is where the multiplying or dividing by the Pythagorean conjugate comes in. I've got a 1 minus cosine. Now if I introduce a 1 plus cosine, the conjugate, and distribute that together, I'm going to have 1 minus cosine squared x. And man, those trig functions keep coming back that we were first introduced to in pre-calculus. 1 minus cosine squared is sine squared. So I'd be getting a little bit closer to being able to finish this problem. So we're going to multiply the numerator and denominator by 1 plus cosine x. And when we do that, we're going to get the 1/2 times the indefinite integral of cosine of x times 1 plus cosine x over 1 minus, let's try getting the phone. So getting back to work, you can tell by the windows that quite a bit of time has come by, but we need to finish this video. Let's distribute the cosine through this parentheses and get the 1 minus cosine squared out and replace it with sine squared. That was from our earlier attempt at a u substitution. Seemed like we needed a sine and cosine together. So we have 1/2 times the indefinite integral of cosine of x plus cosine squared x over sine squared x dx. Okay, well the idea of bringing in this conjugate was the whole idea we needed sine and cosine with this numerator-denominator thing. So let's see if we're good to go now. I'm kind of thinking probably not with those two trig functions on top, but let's just try letting u equal sine squared. Then du is going to be equal to, doing the chain rule, we have 2 sine x times the derivative of the inside function, and the derivative of sine is cosine. So we still seem to have an issue here. I got some cosine functions going on, but I don't have anything where sine and cosine are in the same term. I can take cosine squared out and replace with 1 minus sine squared, but each term is going to have, or no one term is going to have a sine and cosine together. So it doesn't seem like we're done manipulating this until into something that we can, actually go through the integration process through. So, but I do have one term in the denominator and 2 on top. So we talked about expanding or separating the numerator. So let's let this be, I feel I'm going to run out of room here before I finish. 1/2 times the indefinite integral of cosine x over sine squared plus, yes, there's a plus there, so plus, and I'm going to keep the 1/2 through with each of the integrals. 1/2, the indefinite integral of cosine squared x over sine squared x dx. And now that I have it separate, I don't need to bother trying to use substitution again, because as we saw, the derivative of cosine is negative sine, but this is sine squared. I could let u equal sine squared, but then we had that whole 2 sine cosine thing. Let's see. Let's go into that 1 minus sine squared here, and all those integration rules with cotangent. There was a couple that had 2 trig functions in the same expression, so let's let this be 1/2 the indefinite integral of cosine x over sine x dx plus 1/2 the indefinite integral of 1 minus sine squared x over sine squared x dx. Now, cosine over sine is cotangent. And now if I use the cosine over sine to write the cotangent, 1 over sine is cosecant. And that's not going to work that way, because again, letting u equal sine of x, or sine squared x, gives us 2 sine cosine. So this is going to be 1/2 1 over sine squared x dx. And I'm running out of room here, so if you kind of forgive me here, 1 over sine squared, and then as I write the other integral, I can have a minus 1/2, and then sine squared over sine squared is going to be 1, and I'm still actually not going to fit that in there. So let me pause the video, clean this up a little bit, kind of squeeze it in, and show the next line, and then maybe bring in the green board so I have room to finish up this video, or this example. Alright, I just sort of moved that little bit of work over because I want it all on the same board, so when I step out you can copy it. We've got, well actually let's just do this. I've rewritten it, and 1 over sine squared is cosecant squared. And of course, sine over sine, sine squared over sine squared is going to be 1, so this just ends up being the integral of dx. Now, the integral of cosecant x cotangent x is negative cosecant x, and the integral of cosecant squared x is cotangent, negative cotangent x. And then the integral of dx is simply going to be x, and we have our final answer as negative 1/2 x. And then again, with all this integration, don't forget at the end that your plus c. Let me just make sure I haven't written something silly. We got negative 1/2 cosecant x minus 1/2 cotangent x minus 1/2 x plus c. That's the end of almost last example. Coming right up. Last example. We've got the indefinite integral of 7 over 5 times e to the x minus 2 dx. Let's just see if we can go ahead and do a u substitution. If we just go ahead and now say let u be equal to 5 to the e, or 5 times e to the x minus 2, then du is going to be equal to 5 e to the x dx. My numerator, and nowhere else in my problem do I have an e to the x. That's it. So any kind of u substitution, you know, when you take the derivative of e to the x, it's just e to the x. I got a problem. I need to do something in this question where I can set it up so that when I do this kind of a u substitution and I see that du and it's got some kind of e to the x thing in it, I've got an e to the x somewhere else, in this case if I let u be the denominator, somewhere in my numerator to allow me to finish the u substitution. Now I could try multiplying the numerator and denominator by e to the x, but when I do that, I'm going to get e to the x times e to the x is, well, when you multiply like bases, you add the exponents, so it's going to be e to the 2x. And then I'm going to have e to the x times negative 2, which can be negative 2 to the ex. So now I'm going to have, my denominator is going to have two terms with the natural exponential function. So when I go to do this u substitution, now I'm going to need 2 in the numerator instead of just 1. So how about instead we multiply the numerator and denominator by e raised to the negative x power. Now when we do that, we're going to have the indefinite integral of 7e to the negative x over, now e to the negative x times e to the positive x is going to be e to the 0, which is 1, so we're just going to be left with 5 minus 2e to the negative x dx. Now this question is getting very similar, very close to a situation where actually, I think it's really actually there where we can do a u substitution and have it kind of finish up rather quickly. So I'm going to pause, reveal the steps to this one step at a time. If you want, pause the video. I think I just said pause twice. Try it yourself, see how you do, and we'll be back to finish discussing how we can get our answer to match what we might see in a textbook, or maybe we would get from a CAS type calculator that has a computer algebra system. Okay, so we did our, you hopefully got yourself as well, the u substitute, we got a good u substitution, we found the derivative, we were trying to match this, I could have moved the 7 out front, probably really should have, but it was still there, so we moved the 2 over and had 1/2 du is equal to e to the negative x dx, but I have a 7 here, so simply multiply both sides of the equation and we get 7 over 2 du is equal to 7 times e to the negative x dx. So 7e to the negative x dx, 7e to the negative x dx, there's my 1 du. I'm moving my 7/2 or 7 over 2 out in front of the integral. And this wasn't really on purpose, but we once again had a 1 over u or a du over u pattern, and we get 7 over 2 times the natural log of 5 minus 2 e to the negative x plus c. That's awesome. That would be perfectly fine for any kind of standardized test, or if you're not getting points for simplifying, but you might see it in a textbook or a solution guide, or again if you're using a calculator with a CAS system in it, where there is no negative exponent. So at this point you could probably stop the video and just go do your homework. But if you want to get rid of that negative exponent, then that would be 7 over 2 times the natural log of the absolute value of 5 minus 2 over e to the x plus c. We need to find a common denominator so we can combine these two terms. Or maybe that's how you see a solution somewhere, but you could put this over 1 and write this as 7 over 2 times the natural log of the absolute value of 5e to the x minus 2 over e to the x, just multiplying this in the numerator and denominator by e to the x, plus c. And now when you're taking the natural log of a quotient, you can write it separately and have it be the natural log of the numerator minus the denominator. Now this is 7 over 2 sitting out front, and it's only being multiplied to one term. I'm about to split it up into 2, so you want to make sure you use parentheses. And we have 7 over 2, parentheses, natural log of the absolute value of 5e to the x minus 2 minus the natural log of e to the x. Now I don't need to wrap that in an absolute value symbol because e is of course positive. Well, the approximated value of e is 2.718, which is a positive value. Raised to any power is still going to be positive, so no need for absolute value signs there. And of course, this is the natural log, which is log base e. I'm taking the log of a base e, and the log itself has base e, and of course they're going to cancel out. So you might like to include your parentheses, sorry about that. And we have 7 over 2 times the parentheses of the natural log of the absolute value of 5e to the x minus 2 minus 1 plus c. And that is the end of my last example and the end of my video. I'm Mr. True. Wait a minute. What did I just say? That the natural log of e to the x is equal to 1? I appreciate the viewer pointing that out to me. I was getting close to being done with the video and just for some reason said something dumb. The natural log of e to the x is x, not 1. Now, I'm Mr. True. Bam! Go do your homework.